Welcome back to FE exam preparation for mechanical engineers. Today we'll talk about axial loading as it pertains to the mechanics of materials section of the exam. Axial loads are applied along the central longitudinal axis of a structure. Shown here in the bottom left-hand image for the axial load is on that longer axis of the shaft. Stress is defined as force over area. The formula for that is right here. Everything inside the red box on the right-hand side of the screen is a screenshot from the reference manual, and so this should help you get familiar with how the formulas are laid out for the exam. Strain is defined as deformation over the original unit size, which is right here. And the formula for deformation is also laid out here. Strain is unique as it's a unitless variable. And then finally, we'll try to get a different color here. Young's modulus is defined as stress over strain within the elastic region and has units of pascals or psi. This is shown here. I'd also like to highlight that there is a difference between true stress and engineering stress, where true stress is going to be the force over the actual cross-sectional area, whereas engineering stress is going to be force or load divided by the initial area of the specimen. Here's a look at the stress strain curve. First thing I'll highlight here is on the left you have the elastic region. This is the region where as the specimen is loaded, if that load were to be removed, the structure would return to its original shape and geometry. The plastic region is the amount of loading where the specimen is permanently deformed. Within the plastic region, there are also two key regions. The first, on the first half, is strain hardening. So as a specimen is plastically deformed, it actually gets stronger before it breaks, and so that's that region. At the end of strain hardening region, the stress is at its peak, and this is referred to as the ultimate tensile strength. And then the latter half of the plastic region is necking. Necking is where the cross-sectional area of the specimen decreases before a fracture. So it would look something like this. If the original shape was just a rod, it would begin, this is exaggerated, but the diameter would begin to decrease right here. One other definition that you should know when you're looking at the stress strain curve is the yield strength. This is the peak strength within the elastic region before the specimen begins to plastically deform. And it's already denoted here on the chart. Failure is the amount of deformation that the specimen will undergo before it breaks. Failure has many different definitions and classifications. It could be brittle, ductile, fatigue failure, etc. But either way, that is that point. Here's a practice problem. We have an aluminum bar with a diameter of 5 inches, a length of 1 feet, and it's placed under 100 pounds of axial load. How much will it deform? So let's write down what we're given. We're provided the diameter, the length. I'm going to go ahead and convert that 1 foot into 12 inches. And the load I'm going to define as P. And we're solving for deformation. The formula for deformation is going to be P times L over cross-sectional area times E. Let's go ahead and solve for cross-sectional area. That's an easy give me. Area is going to be pi diameter squared divided by 4. We have the diameter of 5 inches, so let's plug that in. is we're going to get 19.635 inches squared. Now we have P, we have L, and we have A. We're going to need Young's modulus. So for that, I'm going to look towards the reference manual. In the materials properties section of the reference manual, there's two tables. The top table says to only use these values if the specific alloy and temper are not listed on the table below. Well, our problem statement is only asking for the aluminum bar. So let's use the aluminum row on this sheet, where the modulus of elasticity, or Young's modulus, E, is 10 megapsi. Okay, now we can just plug in to the deformation equation to get our solution. When we plug into our calculator, the solution that you should get, 6.11 times 10 to the negative 6 inches. Simple problem there for axial loading. Now let's say we were provided a more specific material and we wanted to use table 2. Here we have a rigid horizontal platform is supported symmetrically by aluminum 6061 T6 rod and a magnesium alloy rod, each with length of 12 inches and an area of 1.5 inches squared under 40 kips of axial load. Solve for the amount of load that is carried by the aluminum rod. So this problem is a little bit more tricky than the previous one, but there's two key concepts that are going to help you be successful. First of all, we know that the reaction forces of the magnesium and the aluminum rods need to sum to 40 kips. So the load of the magnesium plus the load of the aluminum rod is going to be equal to 40 kips. The other thing we know is that it's supported symmetrically. So that means that the deformation of the magnesium is going to be equal to the deformation of the aluminum. We used this formula in the previous problem for deformation, so that means that the load of aluminum times the length divided by the area and the Young's modulus for aluminum, oops, kind of doing this a little bit backwards here, is going to be equal to all those same variables for magnesium. And we can go ahead and cross off area and length because those values are equivalent on both sides. The rods each have the same length and the cross-sectional area. And now what we have here is two unknowns and two equations. So we should be able to solve for P aluminum. This is what we're looking for. This should be our solution. Let's solve for P magnesium in terms of P aluminum. So P magnesium is going to be equal to P aluminum times the Young's modulus of magnesium divided by the Young's modulus of aluminum. Let's go to table 2 to find those modulus. For magnesium, we're looking right here. And for aluminum, we'll be looking in this row. Now let's get the specific value we need. Aluminum's going to be this 10 here, and magnesium's going to be this 6.48 times 10 to the third. We need magnesium first, so 6.48. And then aluminum is 10. Okay, so now we've got an equation that represents the force of the magnesium rod in terms of the force of the aluminum rod, which simplifies here to 0.648. I'm going to take this, plug it into my other equation up here, and I'm going to get that the force of the aluminum rod is going to be equal to 1 plus 0.648 equal to 40 kips. Divide 40 by 1.648, and you'll get that the force that the aluminum rod withholds is 24.27 kips. And there you have your solution. So, in summary, axial loads are along the longitudinal axis of the shaft. You'll need to know about stress and strain, which is derived from deformation, and both stress and strain are related by the Young's modulus within the elastic region. Stress-strain curve is a curve that represents how material deforms under increasing loads. There are various regions like the elastic region and the strain hardening and necking regions within the plastic region. You could solve for simple and basic material definitions using Table 1 and more specific materials with the information provided in Table 2 of the Material Properties section of the FE exam reference manual. I hope this helped you feel more confident going into the exam. If you have any questions, please leave them in the comments below. And please also let us know if you'd like to see more topics or have any specific areas. Thank you so much.